All right, thanks very much, and it's good to be here. It's good to still be here. So homological algebra is a wonderful tool. For many of us, it's a way of life. If you work in algebraic geometry, if you work in representation theory, you work with derived categories. They show up no matter where you look. And so one of the amazing observations is that, in fact, homological algebra, as we know and love it, is just one of a giant family of theories. Okay? Moreover, these other theories are interesting and worth studying. And so maybe I'll get to that, a reason why that's true later in the lecture. But for the moment, I want to give an introduction to homological algebra as you already know it, perhaps. But I'm going to give maybe a slightly unusual introduction to it. And then we'll see how it generalizes. Okay? So the usual homological algebra is going to be a theory associated to this ring kx mod x squared. So K is a field. Okay? This is not just any ring. It's actually a super Hopf algebra. Okay? But we're going to get something called Homological algebra, which is associated to any H of finite dimensional Hopf algebra or super Hopf algebra. So I'll explain what that means. But for the moment, and finite dimensional graded. So I'll explain what that is in a moment. But what I'm going to try to do for you right now is explain homological algebra in terms of this ring here. So what do I mean by homological algebra? Okay? Suppose R is a ring. An algebra over this field K. So what do we do with R? So the first thing we do is we look at R modules. Okay? Let's suppose that R is going to be a ring. So we look at R modules, and this is a nice abelian category. Wow, that is loud. And the first thing that we would do when we're interested in dealing with homological algebra is we look at complexes of R modules. I'm going to call this category K of R. Sorry, K of R. So complexes of R modules. Now this is also an abelian category. Given two complexes, you can take the kernel complex, you can take the co-kernel complex. So this is still abelian, and it's graded in the sense that it has a shift, some sort of Z isomorphism, and this is the homological shift. Okay. Now the next thing you do after that, so allow complexes is this step. The next step is kill null homotopy. So there's this notion of a homotopy between complexes, and we'll go into this in more detail. But when you kill maps of general homotopic, you get some sort of quotient category, the homotopy category of R. This category is no longer abelian. Okay? There are no kernels and co-kernels. This doesn't make sense when you kill homotopy. But it is something called triangulated. And a triangulated category, it has a built-in thing called a suspension functor. So it has a suspension functor, which is usually denoted sigma. And in this case, sigma is the homological shift. I just want to make clear that over here, that's a grading, and over here, it's a suspension. In fact, this is also graded, where the grading shift is homological shift. Okay? This is kind of silly, but it will be less silly soon. And the final thing you do is you construct the derived category. And the way that you get from here to here is you invert quasi-isomorphisms. So you have a complex of R modules, and you can take the kernel modulo the co-kernel in each step. Is this familiar to everyone? And you get something called a homology group. It turns out that this doesn't depend on null homotopic maps, so those homology groups are well defined here. And if you have a map between complexes which gives isomorphisms on all the homology groups, then you can invert them. This forms a localizing class, which means that you can formally add inverses to these maps. And you end up with something called the derived category. So I'm going to go into this in more detail soon. But this is also triangulated, okay, and graded, and graded. And it has this homological shift functor, et cetera, et cetera, et cetera. I want to make a little quick point about what quasi-isomorphisms are. Because instead of working with R modules, we could have just worked with plain old K modules, i.e. vector spaces. And we can repeat this entire story with vector spaces. And the reason for pointing this out is that on the level of vector spaces, any map between complexes of vector spaces, which is a homotopy equivalence, that is an isomorphism in this category, any map that's a quasi-isomorphism is already an isomorphism. So actually, this is do nothing. Okay? Quasi-isomorphisms already have inverses. So for just plain old vector spaces, things are pretty easy. Now we have a forgetful map, which just takes an R module and looks at its underlying vector space. And what it means to be a quasi-isomorphism is a statement that is purely understood on the level of vector spaces. The homology is a kernel modulo an image. This is a vector space. And the fact that the induced map is an isomorphism is just a question about it's an isomorphism if and only if it's an isomorphism on the underlying vector space. So quasi-isomorphisms are just the forgetful inverse of actual isomorphisms down here. Okay? So this is the first little sort of statement which isn't usually seen for people who know homological. Now I'm going to go into this in a little more detail and say what everything is. Okay. So a complex of R modules. This is something that we know fairly well. You've got a whole bunch of R modules for each I, and for each integer, and maps between them, which we always call D, and D squared is 0. Okay. But there's another way of encoding this exact same information. So you can take, I'm going to take this ring right here, and I'm going to call it H. Okay? In this particular example, H will always be this ring. H is a graded ring, by the way. So maybe I should write this here so you can keep track of it. H is kx mod x squared, and it's graded so that the degree of x is 1. Okay? Actually, maybe I'll write kd mod d squared. I'm sorry, I should make this a little easier. Kd mod d squared, and the degree of d is 1. So we're going to let A be the exterior tensor product of R and H. Okay? This is also a graded ring where the degree of everything here is 0. So this is also known as R adjoin D mod D squared. And it's fairly clear that something like this is none other than an A module, a graded A module. So complexes over R is the same thing as graded A modules. Okay? And of course, a morphism between complexes, a chain map, is a collection of functors, a collection of not functors, a collection of linear maps such that each square commutes, and that's the same thing as a map of graded A modules. So instead of looking at, so we think of this as R modules, we think of this as graded A modules. All right? So far, so good. Whenever you have something like R tensor H, there's clearly a forgetful functor with A modules to H modules. Okay? So this down here is H modules. Complexes of vector spaces. Okay? This is when R is the trivial. Great. So what is a homotopy? Okay. Let's remind ourselves what a homotopy is. So we've got two complexes, and we've got a map, a chain map between them. Let's call it F. And we say that F is null homotopic if there exists a homotopy, which is a map of degree -1. Okay, that looks like this, such that dh plus hd is F. So if you start at any given spot and you go over, down, plus, down, over, that's the same as just going straight down. Okay? Well, we want a much better way of interpreting this idea. Okay? So instead of talking about a degree map and a homotopy, I'm actually going to talk about projective modules. Okay? So what does a projective module look like? Okay? Or also known as a contractible complex. Okay? So here is the free module. It looks like this. R goes to R by multiplication by 1, and then there's zeros everywhere else. This is the ring A itself, viewed as a complex. Okay? And actually, the identity morphism of this thing is null homotopic. This is sort of a standard fact. Okay? So just to simplify things, I'm going to assume that everything is a complex of free R modules. There's no reason to make this assumption. But just to make life easier, I'll pretend everything is built up out of, is a complex where each one is free. Okay? So, so in that case, you know, you might have a general, this is, you know, the free rank 1 module, but a free module would be something like, you know, V goes to V by multiplication by 1. And then, you know, plus maybe over here, V goes, you know, V prime goes to V prime by multiplication by 1. I mean a free A module. These are free A modules viewed as complexes. Okay. So I claim that actually, I suppose a projective module is one that's where V is a projective R module. So I claim that F is null homotopic if and only if it factors through a projective A module. So let's give a concrete example in this case. Let's suppose that, you know, V is a 2-term complex, just to make life easy. Okay? But in general, you can prove this. And we have this map F. So what I'm going to do to create, I'm going to give myself more room. What I'm going to do to create a projective thing is I'm just going to take 2 copies of Vi plus 1. I'll put them here. Vi plus 1 goes by the identity to Vi plus 1. And I'm going to take the direct sum of this with Vi goes by the identity to Vi. Okay, you know, there's a Wi minus 1 over here. Okay? And so suppose that you have the following map. Okay? So here's the map D. And I'm going to use that also here. Whereas here I have the identity. So you see that this square commutes. Okay? Again, I also use the map. What map do I use here? I also use the identity map. Okay? Now what maps do I use here? I use my original chain map F that I cared about. which is a map from vi plus 1 to wi plus 1. And over here I use f. But then I get a map from vi plus 1 to wi. This is like one of these diagonal things. And I use the map h. Or maybe minus h, I forget. And here I use the map h, so there's homotopy. And you can check that this is a chain map if and only if h is a homotopy from f to the identity. Okay? And the composition of these two maps is really the identity and then f. And if I did things correctly, maybe I need h minus d. So there's some way to do this in such a way that this composition is f. I probably wrote it down wrong. Okay. But it should be easy to convince yourself of this fact. I really want to keep this set of this whole thing on the board for as long as possible. Okay. So, so what's this whole factoring through a projective module business? So, given any reasonable enough ring, if A is a reasonable ring, which includes, say, all finite dimensional Hopf algebras, or actually any sort of symmetric Frobenius algebras, then you can do something which is to take the stable category. Okay? By definition, this is the category of A modules where you kill all morphisms factoring through projectives. This is a weird thing. Okay? Why would this work? So one of the reasons that this setup is nice is that whenever you have an algebra of this form, projectives and injectives are the same thing. All projectives are injective and vice versa. And this is going to help a little, and you'll see why in a sec. So whenever you take a category and just kill a bunch of the maps in it, that's going to completely change the nature of your category. This is no longer abelian. No longer makes sense to take a kernel or a co-kernel. Things are weird. I should have written down the name of this. This is the stable category. Okay. Things that no longer make any sense. But it turns out that this guy is triangulated. Okay? So what does it mean for a category to be triangulated? It means, among other things, that you have some notion of a shift functor. And then you've got this idea of what used to be an exact sequence, what is called an exact triangle now. But I'm going to tell you what the shift functor is. So given an A module M, there is a projective cover. There's absolutely a projective cover, M. A P, whatever it is. This is some map phi. So let's take the kernel of phi. And now we have this short exact sequence in A modules. Okay? So in a stable module, this middle thing becomes 0. Okay? And this thing here, its image in this category, is going to be called the suspension of M. Okay. So it turns out that the class of this object, the isomorphism class in here, does not depend on the choice of projective and the choice of map. Okay? So this is actually a well-defined construction. And exactly as you'd expect if you know anything about distinguished triangles, you sort of always want a distinguished triangle of the form, M with a shift, 0, M. This is always supposed to be one of your distinguished triangles. And lo and behold, there it is. Okay? So this is how you shift in one direction, and I'll show you what it is in complexes in a sec. How do you shift in the other direction? This suspension has an inverse. Okay? To take the inverse, you take an injective resolution, or an injective module that M injects into, one always exists, and then you take the co-kernel. And this thing is going to end up being the inverse shift. Okay? And in fact, you can see, since all projectives are injective, that if you take the kernel, and this is an injective resolution, and its co-kernel is the original thing you started with. So these two are inverse to each other, this operation, thanks to the fact that projectives are injective. Okay. So this is the construction of the suspension functor, and I've kind of given you a hint of what it means to be an exact triangle. And if you don't know what a triangulated category is, you have, this is probably enough for you. And if you do, you can figure out the rest. But let's just quickly look at what it means to do this in complexes, where things are slightly more familiar. Okay? Suppose that I have a complex, and again, let's just assume it's a two-term complex to make our life easier. Okay? I need to find a projective complex that surjects onto this. Okay, well, we've already seen the kind of projective complex that you could use. You have vi plus 1 going by itself to the identity, and then you take the direct sum of this complex with vi goes to vi with the identity. Okay? I just did this wrong. Okay? So, if you have 0 goes to v goes to 0, and you have v goes to v by the identity, there is certainly no map here. This does not commute. This is multiplication by 1, and this is multiplication by 0. This is not a chain map. So I screwed up. However, there is a chain map here, because now this diagram commutes to both the 0 map. So let me just shift this over by 1. Okay? And in order for these squares to commute, this is the identity map, this is the 0 map, this is D, this is the identity map. And what's the kernel of this? Okay? Well, this is something goes to something by the identity. So the kernel is 0 here. Here, this goes to that by the identity. There's something else that contributes as well. So the kernel is going to be some mixed terms. But you can actually see that the kernel is isomorphic to vi. And the kernel of this is obviously vi plus 1. And once you figure out what copy of vi lives in here and what the induced map is here, it's just D. And so lo and behold, what you get as the kernel is the same thing you started with, but shifted to the right. Okay? So the suspension in this case is equal to the grading shift. Although that wasn't kind of obvious from the start. This was not obvious. So the point is that this thing as a triangulated category is the same thing as the stable category of graded A modules. And this thing right here is the stable category of graded K modules. Graded H modules, sorry. Then finally, well, in an arbitrary stable module category, is there a notion of homotopy? No. Okay. There's actually, the one thing that's missing from the generalized picture is actually the notion of T-structures. For those of you who know what that means, there are no T-structures. There's no homotopy. There's no notion of homotopy. But we do have this forgetful functor from the stable module category here to the stable module category here. We can call anything in this preimage a quasi-isomorphism.
Sorry, in the case of general A, what is the bottom line? What are those? What is H?
H is, I mean, I haven't changed what H is yet. H is still, at the moment, is still KD mod D squared. H is KD mod D squared. So this is complexes of vector spaces modulo projective complexes. Yeah. So this is just the normal homotopy category of vector spaces. So in this weird language of KD mod D squared modules, I can't say what homotopy is. I mean, I can take the kernel of D. Okay. I should do this. So because H is KD mod D squared, I can look at the kernel of D modulo the image of D. And this makes sense. This is a thing. This is called homology. Called the cohomology of my A module. And it turns out that if you take something here, then you apply the forgetful functor, then all that you remember is this cohomology. So this is a fact which is very special to this particular H. But in general, I haven't even said what the general fact is yet. But I've already pointed out that to get from here to here, you just have to invert these things called quasi-isomorphisms. Okay. Which are the things that go into the forgetful map. Okay. So this is homological algebra. Not exactly as you know and love it, but it's the same thing. So let's talk about how this might generalize.
Sorry, I thought inverting quasi-isomorphisms took you from CR to DR.
It takes you from CR to DR, that's right.
But you said in the case of A modules DR, then I thought you said DR.
For H modules, these are the same. Okay, for just complexes of vector spaces, a map is quasi-isomorphic if and only if it's homotopy equivalent.
So what is it that remains for, I mean, if we go ahead, what is it that remains for A modules? Where A is half for to be?
I'll get there in a sec. I'll get there in a sec. Okay. You know, so what happens when you do this process? Just, you know, you're taking a bunch of maps in a category and saying, well, let's just add things that are called inverses of these maps. This is not a thing you can always do. Your class of maps that you add it to that you add inverses has to be nice. It has to be called a localizing class. Okay. So these have to be a localizing class in order for this operation to have the correct behavior. Just that was all I wanted to say earlier. Okay. So now let H be an arbitrary, finite dimensional, graded Hopf algebra. And I'll explain what the meaning words are. Missing the Hopf algebra is soon, as I promised. We're going to let A be R, so over K, over a field K. A is going to be R tensor H. And we can repeat this entire top half. So we have R modules. We can look at at A modules. We can look at A graded modules. We can look at the forgetful functor to H modules, whatever that is. We can take the inverse map of the isomorphisms. This forms a localizing class in general. And then we just invert them and we get whatever that is. Okay? So I'm going to call all these things sort of KH of R, CH of R, DH of R, just to indicate that they depend not on the original ring, but also on our choice of Hopf algebra. Okay? And this whole construction can be called Hopf algebra. Let me give you an example, because otherwise you won't see what's interesting about this. So let H be KD mod D to the P.
So R is always a commutative algebra.
Yeah, why not? Sure. It's not relevant. I don't think that's been relevant at all.
I mean, in fact, for going
No,
project
it's not. No, it's absolutely not. So let H be KD mod D to the P equals 0. And for reasons that I will explain soon, I have to assume that the characteristic of our ground field is in fact P. Okay. Or divides P, say. So this is really a prime. So what does an H, and of course the degree of D is 1. So what does an H module look like? Okay, so I've got a graded vector space, dot, 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 and with an operator D on it, which increases the degree by 1. And it's no longer true that D squared is 0. But it is true that D to the P is 0. This is weird. Okay? Very weird. All right. So what does the projective complex look like? So for instance, the projective complex would look like this. Okay? D, D, D. And since this is p-dimensional, there should be p of these things. Okay? So this is this is the free module. Okay? Whereas this, if you just took something that looks very similar, all of these are multiplication by 1. But if this was of some length, I less than p, it's still true that d to the p is 0 on this thing. It's a perfectly good p complex. So these things are called p complexes. Okay. What's the suspension functor? So let's look at this guy of length I. Okay? I need to find a projective cover. So I need to find something that looks like this that maps to it surjectively. Well, here's one. This thing of length p. And this maps 1, 1, 1. And then because this is all zeros, this whole thing commutes. And then I need to take the kernel of this, which is this part up here of length p minus I. Okay? So this thing right here is the suspension of that guy. Okay, so actually, if you suspend twice, you go from something of length I to something of length p minus I, and then something back of length I again. But it's shifted up by p. Okay? However, shifting by once is quite interesting. Okay? Now you'll note that there's also a grading shift. We can also just take a p complex and move everything to the right. Okay? And these things are wholly unrelated. Right? Okay? The suspension does not equal the homological shift. There was no reason, we just got lucky before. Unless p equals 2. Does that make sense? Nonetheless, we have a suspension.
The square of this is equal to p times.
And the square, yes, it is true that this squared is equal to p. That's correct. So that's neat. Okay? Let's see. So there's no notion of homology. There's no kernel of D mod image of D. Okay? There are some things we can do. We could take, for instance, the kernel of d to the I modulo the image of d to the p minus I. And that would give you a vector space that you can extract in each degree that you can extract out of this. And you can do this for each I. So there's no one homology anymore. There's no one thing. But there's many different things which collectively work out to give you a notion of homology. This theory kind of hasn't been well developed. Okay, so many homology functors. Okay, what makes a functor a homology functor in the previous case was that if something has 0 homology, then in fact it is 0. Whereas if something is 0 here, it can clearly not be 0. For instance, this thing, if you look at the kernel of D, and you mod by the image of d to the p minus 1, okay, well actually this is just the kernel of D, okay, so it's non-zero. But there's ways of finding, there are complexes that have sort of trivial operations under one of these things, but non-trivial if you consider the family. So there's some sort of approximation of homology, but we won't be dealing with that at all. The idea is just that there are these interesting Hopf algebras, and when you look at them, you get interesting versions of homological algebra. So, cool. So I claim that everything you could do in homological algebra, you can do in this context too. And there are some people who don't like to start with a ring. They like to start here. Okay, they like to start with the notion of complexes. What do I mean? They like to start with something called a Pdg algebra. Okay? So a Pdg algebra is something for which its modules are already what we might call complexes, but it doesn't come from a ring necessarily. Okay? So usual notion of a Pdg algebra is what it actually is it's a KD mod D squared hop comodule algebra. If you unravel the definition, it's none other than that. What is this? I'm not going to tell you. It doesn't matter. But the point is that you can consider a Pdg algebra, which is a KD mod D to the P comodule algebra, or in general an HDG algebra, which is an H comodule algebra. So for instance, A is an example of such a thing, but it's a very simple example of such a thing, whereas there's many others. And when you do that, you can start with KH of this A, which is also known as, you start with A modules, which is analogous to KH of R. And you just continue the construction. You mod out by projectives, and then you kill and then you invert quasi-isomorphs. So everything you do in normal homological algebra has an analog here.
Where is the co-multiplication being used at all?
Thank you. So there's one other thing that you can do in homological algebra. Okay? And it's tensor complexes. Okay? We learned that you can tensor complexes of vector spaces. When you tensor them together, you get this giant bicomplex. And then you take a total complex and view it as a complex. This whole notion of taking a total complex and viewing it as a complex is using this thing called a coproduct. I'll get to this in a second. For an arbitrary ring, you can't tensor complexes of modules because there's no tensor product of modules in the first place. But you can take complexes of R modules and tensor them with complexes. So there's an action. In general, you can take an R module and tensor it with a vector space. You're just taking a multiplicity space. You're taking, if this is 5-dimensional, you're taking 5 copies of your guy. So there's an action of the bottom on the top by tensor product. And this action continues all the way up. And how does this work? Okay. The idea is that if you have an R module, so because H is hop, H modules are a monoidal category. That is, you can tensor them. Okay? And now I can explain to you finally what a hop algebra is. Right? A hop algebra, well, among other things, it has a multiplication map, a co-multiplication map from H to H tensor H. So in this case, it sends D to D tensor 1 plus 1 tensor D. This is an algebra map, and I'll investigate that in a sec. But the point is that this means that if you take an H module V and another H module W, their tensor product is naturally an H tensor H module, where the first factor acts here and the second factor acts here. But then you have this map here, which allows you to view this as an H module. Okay? That's what coproducts let you do. Let me quickly ask the question, why is this an algebra map? Okay? H, in the case where H is KD mod D squared, I want delta D squared to be 0. It better be. Okay? But I claim this is an algebra map, so this is the same as delta D squared, which is, D squared tensor 1 plus D tensor D plus D tensor D plus 1 tensor D squared, using first, outer, inner, last, as we all know. And this term is 0. And this term is 0. But why would that be 0? Okay. Well, there was this point that I didn't make, that I sort of stated quickly earlier. H is not really a hop algebra. It's a super hop algebra. Okay? And the only difference where the super doesn't make any difference at all in this entire story up till now, except it changes the notion of multiplication in H tensor H. Okay? Changes mult in H tensor H. Okay? Really, this factor here was d tensor 1 times 1 tensor d. This factor here was 1 tensor d times d tensor 1. And these commute in ordinary vector spaces. And they don't commute. They commute up to sign in super vector spaces. So to get, with this d on the left side, you have to commute it past these. These are both degree 1. You get an oddness, and this oddness creates a sign. So this is d tensor d, and this is actually minus d tensor d, and these cancel out. So that's why delta was an algebra map in our usual context. And so when we have Pdg algebras, we're used to these weird signs appearing in various formulas. When we tensor things and take total complexes, there are annoying signs that appear when you take tensor products. And this is all because we're working with super Hopf algebras.
Did you also say that characteristic K would be true in this case?
No, this is for the normal context. K could be any field. But now we're doing this different thing. In this case, it's not going to be super. It's a normal Hopf algebra. We're going to use the exact same formula for delta of d. And we need delta of d to the p to be 0. But this is, d tensor 1 plus 1 tensor d to the p. And now we're in an ordinary category. So there's no signs when we multiply these things. We can just use the binomial formula to get this. And the point is that in characteristic P, almost all of these are 0. Okay? This is 0 in characteristic P unless I is 0 or P. So that in characteristic P, this is just d to the p tensor 1 plus 1 tensor d to the p. And lo and behold, d to the p is 0. So this is 0. Okay? So this is why we couldn't just pretend this was a normal Hopf algebra. We had, over an arbitrary characteristic, we had to set the characteristic to p. And in fact, we can't let this be a super Hopf algebra either, because this to the p won't work in the super context. We really need characteristic p. So even when p is 2, these are totally different constructions. One's a super Hopf algebra, one's a Hopf algebra. They behave differently. So that was where the Hopf came in, was so that we could have this extra tensor product action, which actually is important when studying the theory of this stuff. Like it creates a lot of simplifications. Hopf algebras have really nice structure of their projectives. They have canonical projective resolutions. There's some wonderful stuff you can do. So let me try to give some idea of the point of such a thing. Maybe why don't I give you actually? I'll do a computation first. So here's an example of a Pdg algebra. Okay? Consider the polynomial ring in n generators. Okay? We're going to let d of xi be xi squared. Remember, this is a map of degree 1, not degree minus 1. Okay? We're increasing the length of that polynomial. Okay, so for those of you who this is xi squared d dxi. So I've defined it on generators. I have to tell you what the Leibniz rule is so you can figure out everything else. But this is easy. This is the rule for products. So people used to normal super Pdg algebras, there's a minus sign depending on degrees here. We don't care about that. So for instance, if we want to compute d of xi squared, this is d of xi times xi twice. So this is 2xi cubed. And similarly, d of xi cubed is 3xi to the 4th. And you can do this inductive thing yourself. So what's d to the p of xi? Okay? I mean, what this is it's I times I plus 1 times I plus 2, dot, 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 up to I plus p minus 1 of xi, sorry, what I meant to do was xj to the I. Sorry. Of xj to the I plus p. And you can see that in characteristic p, one of these numbers is 0. And this is the reason why d to the p is 0. Now you can do the exact same computation, actually. You could set this to be some scalar. For any scalar in the base field fp, then this will work. But if you set this to be a scalar in k, which isn't in the ground field fp, then you're going to have a plus I plus 1, and none of these will be 0, and this will fail, actually. So there is some rigid structure here. That was a complete aside. You can ignore it. So this thing is a Pdg algebra. Okay? And in fact, a more interesting one is inside this differential commutes with the action of the symmetric. So you could look at symmetric polynomials inside this. And now you have very interesting formulas. Like the differential of the ith elementary is going to be something like, and I don't remember the signs here. It's something like this minus e1 ei, but with an I plus 1, and there's a plus or minus here. But you have some interesting formulas. Things happen. And the behavior of this thing is depending on whether n is bigger than or less than p. Crazy things start happening. These are some very interesting rings whose PDG structures haven't really been studied that much yet. The PDG structure on symmetric functions, and I guess we've studied it to some degree. No, this is new stuff. Let's look at this particular subexample, which is just a polynomial ring in one generator. So what does this ring, which is a Pdg algebra, so the ring itself is a p complex, look like as a p complex? So it's got the identity living in degree 0. It's got x living in degree 1. It's got x squared living in degree 2. And it goes on forever, yes? How does the differential act? The differential of the identity is 0. The differential of x is x squared. The differential of x squared is 2x cubed. And this continues until we have x to the p. And the differential of xp is px to the p plus 1, so it's 0. That's why this is a p complex. So then this stops. And then you have, again, starting again at xp plus 1, it goes out by multiplication by 1 up to x2p. And then the differential of that is 0 again. And this repeats forever. I should have put this underneath that. I feel bad. There. OK? So in fact, this bit, this bit, this bit, this bit, all of these are contractible p complexes. They're all free. Right? They're all length p. OK? They all disappear in the stable category, or in the stable category of H modules, not necessarily in the stable category of this ring modules. Okay, certainly in the derived category they disappear. So in the derived category of modules over this, you're just thinking everything's a vector space, and if it's contractible, then you kill it, and all of the parts are contractible. So as a p complex. As a p complex, the inclusion of the identity subring inside this is a quasi-isomorphism. Okay, when you cross up all this stuff, all that's left is the identity. And that actually tells you that actually the derived category of this ring is isomorphic to the derived category of the ground ring. So this is the kind of computation you can do in p-homological algebra. And now we'll get to a computation that you can do in normal homological. All right. So there's an example. of something you can study at. Now I kind of want to say why we care about this. So, given an abelian category or a triangulated category, you can take something called the Grothendieck group. Okay, so to an abelian or a triangulated category, you get a Z module. This is a construction called the Grothendieck group, and it basically records just the information about the objects. What are the objects and how do they take direct sums? So what it does, this thing is specifically what you get is the free Z module generated by objects in C, modulo the relation that if you have a short exact sequence, that the class of the M2 is class of M1 plus the class of M3. This is what you can do with an abelian category. In a triangulated category, you do the same thing except with distinguished triangles. However, for the Grothendieck group, the growth group of a triangulated category, the action of the suspension functor, so the class of the suspension of M, is always minus the class of M. And the reason is that there is this distinguished triangle that looks like this. And therefore, this plus this is 0. So this is always a fact in any triangulated category. So now, suppose you have a graded abelian category, or a graded tricategory. If you take its Grothendieck group, it's naturally a ZQQ inverse module. Okay? Where you say that the class of M grading shifted by 1 is just Q times the class of M. Grade shift by -1, you get Q inverse. So in our normal context, the grading shift is equal to the homological shift. And so this factors through Q equals -1. But for homological algebra constructions, they're different.
What you just said.
Right. So in normal homological algebra, and I will write it down, as I might as well. So for H is Kx mod Kd mod d squared in the superworld, the suspension is equal to the grading shift. And that means that in the Grothendieck group of, say, this homotopy category of R modules for any ring R, we have that Q is equal to -1. It has an action of Q. It has, right? But it turns out that Q always acts by -1. Okay. However, this needn't be true for general H. And in fact, in general, there's no relation at all between the grading shift and the homological shift, and the suspension.
So that means, so you're saying that the ZQQ inverse module structure goes via the evaluation?
Yes, that's correct, exactly. So it is ZQQ inverse module, but Q equals -1. Let's look at what happens for K P d mod d to the P. Okay, for K d mod d to the P, let's just look at the Grothendieck group of its homotopy category. Okay, so the point is that any K d mod d to the P module has a filtration by one-dimensional modules. Okay, I mean, it's a graded module over this graded ring. You know, there's only one graded simple module. It's the one-dimensional module. There's only one one-dimensional module. Okay, so this one-dimensional module, you know, which is K in some degree. Okay, these things span the Grothendieck group. Okay? So in fact, as a Z module. So in fact, just k in degree 0 spans as a ZQQ inverse module, since this thing is q to the I times that. Okay? But there's a relation. Okay? And the relation is that the class of this contractible complex is 0. This thing has length p. And what does this say? This says that, but the class of this is the class of the boring one. Let's suppose that this starts in 0. Okay? The class of the boring one times 1 plus q squared, dot, 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 up to q to the p minus 1. Okay? So whatever q is, however q acts, it has to factor through 1 plus q squared plus dot, 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 dot equals 0. Okay? In fact, for any R, or in fact for any Pdg algebra A, you have this action of the ground guy by tensor products on this other homotopy category, so CHR or A stable modules. And so if you take any module and you multiply it this many times, then this is like tensoring that module with this complex. And it's contractible when you get 0 in the Grothendieck group. So therefore, that module times 1 blah, 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 blah is 0. Okay? Thus, 1 plus q squared plus q to the p minus 1 equals 0 on any Pdg Grothendieck group. Okay? So what is this thing? This is the characteristic polynomial of the p-th root of unity. Okay? This is the algebraic condition that q is a primitive p-th root of unity. So our statement is that the Grothendieck group of any Pdg category, or also the derived category, is naturally Z adjoined a p-th root of unity module. Okay. So this is sort of the first way in which p-th roots of unity have been categorified. So this whole idea was all due to Kovanov. Everything here is due to Kovanov. Although he was inspired by certain other things. So I'll give a little bit of history after I state the punchline. So the punchline is that we now have really nice algebras. We have these new algebras, which are suddenly burst onto the map. These things categorify, say, quantum groups of Lie algebras, or maybe Hecke algebras of Coxeter groups, or maybe Heisenberg algebras, et cetera, et cetera. So what does it mean to categorify? It means you have a monoidal category, and you take its Grothendieck group. It's a ring. It's a graded category, so its Grothendieck group is a ZQQ inverse algebra. And it turns out that this algebra is isomorphic to this ZQQ inverse algebra. Okay? So you take the category of modules over some fancy algebra, take its Grothendieck group, and it's something that we used to love. Okay? You know, no, this is right now, I'm just saying what was already done as ZQQ inverse algebras. Okay? So now there exists a structure. So again, this is proven and conjectural depending on which context you care about. There exists a structure of a Pdg algebra on all these algebras That is, for each algebra, we can find a differential satisfying this Leibniz rule with d to the p is 0. And now they categorify these things at roots of unity as z. Okay? So this is fantastic, because categorification at root of unity was actually always the point of categorification. Or when it was originally decided, when this term was originally coined by Kren and Frenkel, their dream was to categorify representation theory at a root of unity. And this dream is beginning. So I guess it's 3. I started a little bit late. I wanted to give like 1 or 2 words about the history of this.
Okay.
And it's just going to be writing down some names on the board. So as far as the actual mathematical history of this modern approach to homological algebra, okay, the whole idea and initial development was due to Kovanov, although he was inspired by conversations with Bernstein. And then, like, the sort of deep homological algebra in this context was mostly developed by a recent PhD named Chio. I think this is his last name and not his first name. So basically, like, everything that was done in normal homological algebra, he did this. So perfect complexes, all the usual tools, cellular filtrations. He developed this sort of the theory of these things. And sort of taking categorifications of UQ plus into roots of unity, this was done by Kovanov and Chi. And then taking the categorification of the whole quantum group to root of unity, this is done by Chio and myself. So this is where I come in, and we're still developing this. There's a couple of new techniques that you had to develop in order to do this. One of the amazing facts is that the Karoubi envelope of a Pdg algebra is not Morita equivalent to the original Pdg algebra, which is very, very different from normal homological algebra. So it's quite tricky. But then there's some interesting history, which is that where did complexes originally come into being? Topology, right? Chain complexes, simplicial homology. Okay? So when you originally do simplicial homology of a topological space X, what you construct are these complexes of simplices or dual simplices. And you can construct these face maps. This is sort of the face map. Okay? And these face maps had annoying signs. Okay? This is why we use simplices. They're oriented and so forth, so we could put signs on things so that everything works. And we all remember when we were a grad student learning this and how annoying it was. But these signs guarantee d squared is 0. That's why they're there. Okay? Well, it was originally observed even back in the 50s, and when like a lot of the categorical development of this was rather new, that if you ignore the signs, but work in characteristic P, that d to the P is 0. So this whole idea of P complexes for simplicial homology is, I think, due to Meyer in the 50s. And in fact, a much more modern approach to N complexes at non-roots of unity, but using sort of quantum numbers instead, is due to, I believe, Kapranov, much more recently. So the problem with this, and the reason that it was utterly forgotten and disappeared, is that some guy named Spanier came around, one of these sort of category theory people, and proved that you get nothing new. In other words, you take a topological space, you take its P-complex simplicial thing, you take these various like kernel of d to the I, mod image of d to the p minus I things. These can all be reconstructed from the usual cohomology. So you gain no new information. And the way that they prove this is some sort of like, abstract nonsense that whenever you have something you can do to topology and it satisfies certain axioms, then it must be this. So they proved this, and it kind of shut down the theory, and people forgot about it entirely. But of course, the problem is just that these are the least interesting P complexes in the world, and that somehow, by taking interesting Pdg algebras, you get much better ones. So it's back with a vengeance. And that's all I wanted to say.
Why can't you do such a thing by instead of using plus everywhere, you put roots of unity there?
Yeah, so
And
that's
assume that your ring has roots of unity.
yes. So that's basically what Kapanov does with n complexes. Yeah. But there's sort of the homological theory of that hasn't been developed at all. I don't think the growth in the group is that easy. So you need to do some sort of development. Like what is a homotopy? What is that whole structure is not really there yet. I don't know actually though. I'm not an expert on that. I've never actually read this stuff.